Guru, what does it mean to be a distinguished engineer?
The ability to fail without fear.
So 30% then is a very high rate, and that's the rate of a distinguished engineer is what you're saying?
Yes, pretty much. A good year for me is I start one or two projects and I get one success.
To use a perspective from the animal kingdom, lion, the king of the jungle, is at 20%.
Yes.
So you're higher than that. Let's talk about the classical, design challenge that chip design and EDA had, scaling, right? What is a high-end design that is around today? How many transistors?
It's already surpassed 1 billion transistors 2-3 years ago. The chips at a certain point, you really can't add more devices. It boggles the human complexity, right? Because at the end of the day, it's the human designer that has to sign off on something, that has to be, there's software that has to verify if the chip is actually working. So now you're talking about splitting the chips up into different chips and then using different technologies to be able to integrate them. This was the PowerPC Consortium, right?
Yep.
So it was a collaboration between Apple, IBM and Motorola.
Yeah, AIM, right? As they called it.
Yeah. We had this building where we had this collection of people, right, from all the three different organizations, completely different cultures, and we were expected to build, the 603, 604, 620, right? That was the series, the PowerPC series. And what was really interesting was, so I come in the first day and I go looking for my manager. I ask him, okay, so what do we need to do, right? He says, you need to go walk the cubes, talk to the designers, ask what their problems are, and figure out how to solve.
Today we are joined by Guruprasad Rao, a distinguished engineer at Cadence Design Systems. Cadence is one of the world's leading electronic design automation companies. Over a career spanning 3 decades, Guru has played a central role in shaping technologies that power modern electronics and systems. At Cadence, Guru has served as an architect, senior architect, and now a distinguished engineer, a title that represents not only technical mastery, but also leadership, mentorship, and influence over the company's global innovation strategy. In this episode of the Influence Show, we'll trace Guru's remarkable journey through industry-defining companies, explore the changes and opportunities in EDA today, as well as semiconductors. We'll also uncover what it means to hold one of the most prestigious technical titles in engineering. Guru, welcome to the Influence Show.
Thanks, Manish. It's a pleasure.
Guru, when people ask you what you do, how do you usually explain your role?
It's not easy, right? So when if your dad asks you, why do you make money while you're sitting on a chair and staring at a screen? How do you explain how much software has changed, what the world that we live in is, right? So my job is to kind of, if you look at EDA, there's a lot of software and the software has a long lifespan. And there's a lot of change happening in the industry all the time, right? Technology is changing, design styles are changing, what people expect out of electronics is constantly changing. So the tools have to keep up, right? And often these are big jumps which require big changes in the tools. So typically my role is to react to those changes that's happening in the industry and kind of rejuvenate the tools so that they can now handle the designs of a larger scale. So dealing with complexity and scalability is how I would explain it, but to anyone who is not really familiar with EDA, it's hard to explain.
So you're essentially designing the tools to be able to design the chips and the systems and so forth that will come out in a few years. So it's a precursor to all of the electronics that's going to come out or is coming out.
Right. So you can view us as like the people writing the AutoCAD software, right? We're not the architects, but we are the people who are providing the architects the tools to be able to design the buildings. So similarly, we are providing the tools for designers from companies like Intel or Apple or any of these big guys who design chips to be able to design the software. People can't do it by pen and pencil anymore, right? It used to be these big boards where people would sit down and actually trace routing connections on the board. And you just can't do that anymore because you're talking about billions of devices on a very small area. So you need software that is designed to be able to handle all of this. So yes, that is basically what we do as a company.
So that era where things were done on pen and paper and large boards was what, in the 1950s and the 60s?
Well, I would say 60s, 70s, right? Or even up till the 80s, you're talking about, if you look at Cadence's origin story, it is a combination of companies that led to, essentially the founding of the commercial EDA industry, right, in the late 80s. And the primary software that was the genesis for Cadence was essentially drafting software, right? So this was software that people used to essentially mimic the notion of drafting. And so this is all the changes that we have seen in terms of the move from, the physical world into the computer world is all in the last 25 years.
Guru, we'll talk about that journey a little bit more since the early days, because you've been part of this industry for a very long time, right? So we'll talk about that. Guru, what does it mean to be a distinguished engineer?
The ability to fail without fear. The nature of software, right, is that it is very hard to get right because there are so many degrees of freedom, right? There are so many things that are changing. There are so many things under your control. And it is very hard to meet a set of requirements because requirements are changing and the software gets larger and larger. So the big challenge is, finding that sweet spot, right? And it takes multiple tries, right? I've done about 20, 25 big projects in my career. And I would say maybe 7 or 8 of them have been successful. So I'm talking about a hit ratio of 30%, right? So in most industries, I would have been out of a job long time ago, right? But that's the nature of software. It's so easy to do because it doesn't require much, right? It requires a computer, it requires your mind, but it's easy to get it wrong. And you have to try different combinations, you have to try different strategies until you get it right. So I think part of what happens as you move up the technical ladder is that you have the leeway, right? In most of these technical companies, right, not just Cadence, in most scientific companies, you have the leeway to experiment and to try to, change the frontier, right? So that's basically what my role is a big change comes in, I have to take this large complex piece of software that might have been around for 25, 30 years and figure out where the vulnerable spots are, figure out how to change either the data structures or the strategies or the algorithms, work with other people, right? Collaborate with people and figure out how to extend the life of the product.
Something that was developed over a span of 20, 30 years, right?
Yeah, most of the tools that we have are still tools that were developed, started in late 80s. A tool like Virtuoso, which is our, flagship IC design product that started in early 90s, and it probably has pieces of software that came in from an acquisition that was the genesis of Cadence, right? Same thing with the current tool that I'm working on. It's, again, software that goes back to the mid-80s. There are still copyright signs with 1984.
Awesome. So 30% then is a very high rate, and that's the rate of a distinguished engineer is what you're saying?
Yes, pretty much. I mean, 30% is a good year for me is I start 1 or 2 projects and I get 1 success.
So to use a perspective from the animal kingdom, lion, the king of the jungle, is at 20%.
Yes.
So you're higher than that. Fun fact. Now, Guru, do you see yourself more of a problem solver or an innovator or a mentor or all of these and more?
First and foremost, a problem solver, right? My job is to, like I said, react to a challenge, and that's what I enjoy doing. It's not necessarily innovate in the classical definition of coming up with something new. I'm not a researcher, I'm a developer, right? So my focus is on problem solving, and I enjoy working with people, and I enjoy telling stories. I enjoy sharing the process, talking about the process of development and collaboration. So I like, working with young people. So I would say problem solving and being a mentor are two other things that I enjoy most.
When do you get pulled into problems? Right when they appear or when they've been boiling?
Well, if you look at EDA companies, we are often further down in the food chain, right? I mean, you have innovations in materials, right? And, I saw your interview with Dr. Chadda last time.
Yep.
And he was talking about all the innovations that are going into materials, right? So that's where everything starts, is when there is a big jump in the ability of electronics to provide more performance, more functionality per same area. Everything downstream has to react, right? So typically that materials work is going to go into the foundries. The foundries are going to start coming up with new processes that reflect the physical and electrical characteristics of those materials. And at some point, designers will start asking us to provide tools that can handle that kind of technology. That means, for example, the number of devices that you need to support. That's typically our problem, right? Scalability. Suddenly, the number of devices that you need to support has gone up by order of magnitude. And the same software, the same ideas that you use to build the software in one regime don't work in another regime, right? It's not performant anymore. It doesn't fit in the memory that you have available. So you have to react to it. So that's when we get involved. So typically it's customer driven, right? I mean, EDA, if you're familiar with this industry, right? For a long time, it was relatively static at about 4 billion, right? There were 3 or 4 major players, a lot of small players, but this TAM, the total available market, was stuck at 4. In the last 10 years, it has grown to 14, right? So it reflects this growing role of electronics. It reflects the growing number of people who are using the software, right? So we've gone from maybe 1,000 customers to 10 million customers. And what that basically means is, the strategies that we were using for serving a small customer base is very different, right? Because now it's becoming like a commercial, more a software that is dealing to a much larger market. So I think, we are often dealing with those kinds of issues, and that's when we get involved.
I mean, scaling has been the constant, right, in the industry, in the chip design industry for a very long time, right? But this is like additional degrees of freedom, right, with more number of customers and scaling of customers themselves, right? Because what you're essentially saying that it was like an industry that was limited to say 4 billion, right? And now it has grown significantly. So the number of designs being, taped out, and all of these. This is such complex software that you'll run it, and you have to provision for all the design work that's going on, right?
Well, exactly, right. So I think the big challenge is this. It used to be that we could design to a few what we call PDKs, right? Yeah. So there were a few foundries, you could design to those. But now, if you look at, again, and this goes back to what we talked about earlier in terms of the explosion of innovation in the material side, you have all kinds of new technologies, right? You have, glass as a medium, you have panel level displays, and you have, because as electronics starts getting into more and more of our physical life, you need different form factors, you need different materials that can be rigid, that can be flexible, that can be, that can form fit into all kinds of spaces and nooks and crannies of the physical world. you're talking about a completely different technology where it's the same designs, but now being imprinted on maybe bendable plastic, right? Now that's a big jump for us, right? You're talking about software that was designed for a planar surface that is handling a certain number of devices, and now you're talking about form-fitting curved software, curved surfaces, where it is no longer straight lines but geodesic lines, and that you have to worry about all your geometry algorithms in your software change. So these are big jumps. So technology, I think, works in lots of ways to completely perturb the EDA ecosystem, right? And what that basically means is that we have to react to it by, doing heart surgery, right? Changing the internal algorithms to be able to handle, a different regime. So lots of changes from not just, and the scale is not just number of devices, it is where the devices go, what kind of devices they are, right? Are they horizontal? Are they vertical? Right? FinFETs, that's a big challenge for us because you're talking about a third dimension.
Yeah.
Heterogeneous integration, another big challenge for us because now you're talking about chips that are going to be able to talk to each other directly, right? Without being mounted on a board. So all kinds of challenges that show up that turn out to be big challenges for EDA.
Let's talk about the classical, design challenge that chip design and EDA had: scaling, right? The process scaling itself. What is a high-end design that is around today? How many transistors, Guru?
Well, if you look at digital chip, right? It's already surpassed 1 billion transistors 2-3 years ago, right? If you look at some of the newer chips, you're probably talking about even more. But the scaling is the chips at a certain point. You really can't add more devices. It boggles the human complexity, right? Because at the end of the day, it's the human designer that has to sign off on something. There's software that has to verify if the chip is actually working. So now you're talking about splitting the chips up, right, into different chips and then using different technologies to be able to integrate them.
Chiplets and stuff like that.
Chiplets, right. And chiplets are, again, you could design these chips typically in isolation and put them together, but now chiplets interact so much with each other that they have to be co-designed together. As soon as you get into that regime, now you're talking about sudden jump in scale again, right? Because even though a single design is limited to maybe, 1 billion transistors, you have multiple of these, right? And these could all interact with each other. So that's another big, scale issue for us. So yeah, I mean, I don't see that dropping. So yeah, Moore's law might be flattening out on a single device, but the number of devices, the way in which these devices are arranged with each other, you can embed these devices into substrates, right? All of these are going to be happening all the time, right? So designers are going to have this huge challenge of how can I put all of this together and see if it actually works, right? And that's where our software comes in. Is it's too expensive to build it and see, so you have to model it and run it in our software. So a typical 18-month cycle for a complex design like a microprocessor, you're going to spend 12 months in EDA tools, right, in the virtual world before you actually get to actual silicon.
How large is a typical piece of EDA software that could be used in production?
It varies, but I would say 50, 60 million lines of code, right? Lot of which, there's a hidden secret about EDA software, right? Code can come in but never goes out because you never know who's using it, right? Typically, customers are very careful about telling you what features you are actually using, right? Whether they are actually using a certain feature or not. So you can't take out features because you don't know who's going to complain, right? So end-of-lifing features is not easy. So everything accumulates over time. So you would say, a 30-year period, typical life cycle. Every year, you're probably writing about 1.5 million, 2 million lines of code across the entire organization. 50, 60 million lines of code.
30-year cycle? That's what customers are promised?
No, but software, again, for software to have survived that long, it is because it was useful.
Yeah.
And so when software is useful and it is complex, people take time to learn it. And then when people take time to learn it, they don't want to give it up, right? They don't want to move to something new. So it takes that kind of stuff builds up, right? And typically you have, organizations, 200, 250 people, software organizations, they're generating about 1 million lines of code, 1.5 million lines of code a year.
How do you get 60 million lines of code to work?
Basically, you have to have regression. You do all the hygiene related stuff for software. You have big regression test banks. Every change has to go through some kind of smoke test cycle, some kind of regression cycle. This is not like commercial, like Microsoft Word or something like that, right? I mean, they are much more careful and they have longer design cycles and they have a lot of people. We have traditionally been not as focused on testing as we should have been because we haven't had that many customers, right? Our focus is more on allowing designers to catch up with whatever technological change is coming. So the focus has been on delivery more than on the correctness of the software. But like I said, as the number of customers increases, then we become more like a Microsoft, right? Where we have to be much more rigorous about testing and all those things. And so, yeah, at that point, it will start getting harder and harder. But yeah, you have to make it work.
Awesome. Guru will talk about that in a little bit more detail on the kind of problems you work on. But let's go back. So Bell Labs in Murray Hill.
Bell Labs in Murray Hill, yeah.
The global headquarters.
Yeah. I mean, it's much more impressive in retrospect because at that time, it was, there were a lot of changes already happening. We had Carnegie, Dennis Ritchie and
Yep.
Carnegie and, the Professor Gumbel and Poon, right, the transistor models. And I remember he would be on the same floor as us, and he must have been in his 80s at that time. He would still be the first one to come in and walk down the corridor and stop by everyone's office and say good morning. And this is Gumbel and Poon, right? So it's Professor Gumbel, and he would still be coming in every morning, and he would still be doing interesting work. There's Al Dunlop, who was one of the early pioneers in CAD. He was on the floor above us. So yeah, in retrospect, I think about that and I go, wow, that is a pretty great experience. But at that time, you go into work, you do your work, you come home.
I mean, if we use one word to describe, that organization, is iconic.
It is. It is pretty amazing. And it's a pity that organizations like that are not there anymore. And I could see the change happening while I was there itself, right? Commercial EDA was coming into play because that was still the days when every design company had to have an EDA wing, right? Because EDA was in-house. So we were the in-house EDA for AT&T. And so all their, big telecommunication systems were eventually built with EDA software that we were developing. And some of that software actually is still around, right? Cadence eventually bought part of Bell Labs. But that whole experience was transformative because the first time you really sit in a space with peers and with your seniors who are focused solely on getting the job done, right? I remember 3 months into my job, I walk into a meeting and I present something. And one of the guys gets up and says, when you have something interesting to say, call me, and walks out of the meeting. That's a tough environment. You better get good soon.
At that point, then every company that was building chips or equipment were doing the EDA tools in-house.
Pretty much, yeah. Cadence was just starting up. They were acquiring in early 90s. They acquired Gateway Design Automation, which is where Verilog came from. Synopsys was getting started. So they were all trying to, displace internal EDA, right? So, and I think by the mid 90s, both these companies had become big enough that it was now, less economical for these big design companies to do their own EDA. And EDA had become specialized enough that you couldn't just do it with electrical engineers anymore, right?
Yeah.
You needed software expertise, right? So, as I said, the software was getting much bigger, and most electrical engineers are solving problems, right?
Yeah.
They're not building solutions.
Yeah.
So that only goes that far. So it was just a matter of time before you had the growth of commercial EDA companies, software companies, whose focus was building the software, not on the designs themselves.
And did you wear a tie and jacket back then?
No. Jeans.
I see. I see. So the times had changed, right? That was a few years earlier that software engineers and engineers used to wear a tie and jacket, right?
Never been in a job where I had to wear a tie and a jacket. So.
Okay, awesome.
Now, I remember you were in Korea, so I'm sure you had to.
Yeah, I mean, it was very interesting in Korea. Now that you ask me, us engineers wore, jeans and shirt probably, not t-shirts. But the higher ups were dressed like people working in a factory. They had a dress on. And that kind of demonstrated, so they had like a brown jacket and brown pants. Honestly, they looked like a line worker, right? I think those were the dresses. But I think that kind of demonstrated that they've been around for a very long time.
So you had to earn your way to not wearing a suit.
Yeah.
Okay.
Yeah. That's my memory of Korea, and I'm talking about 2002. 2003 Samsung is when I started working there. So all the Sangmus or the VPs, right? They all came in black executive, cars, like Countrymen or whatever, right? They had their assigned spots in front of the building, but when the person came out, they were in the dresses of factory line workers, which was interesting. Now, Guru, you joined Motorola in 92, 93. Doing 603.
This was the PowerPC Consortium, right?
Yep.
So it was a collaboration between Apple, IBM, and Motorola.
Yep. AIM, right? As they called it. Yeah.
So we had this building where we had this collection of people, right, from all the three different organizations, completely different cultures, right? And we were expected to build, the 603, 604, 620, right? That was the series, the PowerPC series. And I was writing the software, some of the software for 603. And what was really interesting was, so I come in the first day and I go looking for my manager, and I meet him and I ask him, okay, so what do we need to do, right? What do I need to work on? He says, you need to go walk the cubes, talk to the designers, ask what their problems are, and figure out how to solve it. I loved it. In the beginning I was taken aback, but the notion of picking your problem, right, and choosing how to solve it and seeing it actually work on a design was incredibly fulfilling. So during the 603, I used to live in San Antonio, and this was in Austin, right? So I used to drive an hour and a half to work because my wife was teaching in a university in San Antonio. I spent a week during 603 tape out in my cube with I had my sleeping bag and I was there. And all I would do is sleep and code, sleep and code, and send out releases of software. 3 releases of software every day.
3 releases a day?
Yeah. So, yeah, that was an amazing experience. That was 603. I was there for a year and a half.
But 603 was a complex design. It had superscalar, out of order.
It did. It did. And I was working on this software called, it is basically a timing budgeting software. So you would get your timing reports from your static analysis, and then my software would go in and distribute the slack and reset the constraints, and then the designer would resynthesize. And essentially it is a flow planning exercise, right? Because you're basically doing moving logic around different blocks until you get your overall timing right. So this was 3 releases of software every day.
Then you did that, and then at Symmetrics you did test equipment.
Yes. So one of the guys, so, you know, 2 of the guys will come later in this conversation, Curtis and John. So Curtis went to Symmetrics because he knew the owner. It was a private company run by one guy. And it was test equipment, building the test equipment for any kind of electronics, right? Whether it was, and not just electronics, but also software, right? So whether it was a digital tester, whether it was a washing machine, whether it was a phone, whether it was a flight simulator, he would basically take contracts from companies, and we would write the testing software for it.
Again, you got exposed to so many different use cases, right?
Oh, absolutely. It was, again, another one of those big changes, right? I mean, the first time you really see, I mean, in software, we are so insulated from actual usage, right? I mean, these days, of course, the people who write the iPhone software can see how consumers are actually enjoying it, right? But those days, our software was used by devices, that was used by companies, that was used by somebody else, that eventually went into consumer electronics, right? So having that direct connection from seeing the fruit of your work end up and seeing the actual consequences of that was, again, a big change, right? Because you realize, again, you know, we were talking about the degrees of freedom in software, right? Very easy to get it wrong. You're always limited by the amount of time that you can put into testing the software. You come in there. So, for example, I was sitting in a hangar in Oklahoma at late in the evening, and we were testing our flight simulator software, and we boot it up and it doesn't come up, right? So the whole trip to Oklahoma was wasted. We had to go back, do the whole bring up testing again, check it out, and go make another trip to Oklahoma. And the second trip, it actually came up, right? And so that whole notion of how much, you know, you are leaving on the table, right, in terms of reliability, really gets driven home fast when you are the one seeing the consequences of what you have not done, right? So that whole idea is again something that every software designer should go through, is understand what it means to not spend that extra day testing, right? What it means to not spend that extra day thinking about all the cases that could come up, right, that you haven't thought of. You're never going to be able to do all of it, but it all shows up in the real world.
So the first EDA company in Austin, the year is 97, and by then the mainstream EDA was based out of Silicon Valley?
Yeah, pretty much. And yeah, so Cadence and Synopsys had a presence there, but all the development was here. So we were the first in Austin. So we were able to bring in a lot of people. So we started from 3. The 3 of us grew to 70 people, and then contracted to 35 people. Painful experience. Hard to let go of people whose families you know, right? who you spent so many hours with at work. But then we got acquired in 2003.
Let's trace that journey a little bit. So this was the next step in you being independent, right? I mean, you said
Yeah.
that you first became a consultant, you know, and then it takes a bit more courage to actually go start a company, right? How did that happen?
I don't think it was hard for me. It was hard on my wife, right? It was hard on people around me, but not hard for me. I mean, I've been blessed with a lack of fear, right? So it is. I don't look too far into the future, right? I do what I think, what I see is interesting at this point in time, and that has served me well, right? So for me, it was just the next step. It sounded interesting. John and Curtis were telling a good story. There was a purpose around which I could frame my daily existence around, right? All sounded good. So it wasn't a big move for me. And it was, like I said, John built PCs from scratch. I was putting furniture together. We were hiring people. We were doing things that startups do, right? Do what it takes, like you do on a daily basis, right? Do what it takes to get to the next day. And yet be able to kind of look at the bigger picture and say, okay, where will I be in 3 months, right? You can't think about a year, that's too far ahead, but, where will I be in 3 months? So just that whole process was, again, big, enriching process, right? It gives you the confidence that you can deal with a lot of things. You meet lots of different kinds of people. You have to figure out how to get, more out of people. You have to figure out what it takes for you to change. I used to start off with this notion of some kind of absolute scale, right? This notion that you either cut it or you don't. But over time, you realize that it is all about dealing with a person on a person-to-person basis, right? You meet someone, you talk to them, and if you can leave them a little bit better and they can leave you a little bit better, you both have come out ahead, right? It is not about defining some absolute goal that either of us have to reach, because you may not be right and the other person may not be right. So again, that kind of transformation happens when you are in that kind of startup environment, right? It's a high pressure environment. You don't know whether you're going to meet the next monthly paycheck for people, right? And that's a big responsibility. So you have to make some decisions around, whether to spend time on getting the deal with a customer or, writing that, 100 lines of code that might help with next year's software. And all of these have immediate impact, right? Things that up till now had always been a little abstract to me, suddenly became very concrete. So, and I think for all of us, all three of us, it was that kind of experience. Meeting venture capitalists, right? Like I said, I was the only brown guy, right? So two white guys and a brown guy would go into a VC meeting, and people would come up, shake hands with the white guys and not with me, right? Not necessarily because, and in the beginning, you get upset about that until you realize that it is less about them and more about you, right? At some point, I realized that it was something that I had to do. So when someone would come up in a meeting, I would be the person stepping up and putting my hand out. They don't have a choice, right? And it's not like they're hesitating to shake your hand. But if you are kind of slithering to the back, when these two guys step up, they won't shake your hands, right? So those kinds of changes happen, right, in an individual, and it really tells you that the onus is on you, right? The world might not be fair, but the onus is on you. You have to make it happen.
That's a very powerful and interesting thing, Guru. You made the change in yourself rather than expecting the world to change, and that would have frustrated you, right, or made you angry, right? But you
Yeah, it did.
changed your own actions, right?
It did. So you have to have a little bit of, self-reflection, and because that's what you can control, right? You can't control the outcome. You can only control the effort, right? You can only control what you do. You can't control how people react.
You guys were pretty successful with raising venture capital, right? At least you had
Yeah,
certain degree of
we went through
success, right?
5 rounds of investment. We raised over $30 million. And yeah, we exited in 2003. We were acquired by Magma. And we became part of Magma. Magma actually started their custom business unit around, acquiring us and a company called FineSim from Korea, which was a fast spice simulator. And FineSim actually still survives, as does Silicon Smart, which is our software, because eventually Synopsys acquired Magma, right? So the characterization software in Synopsys is based around Silicon Smart and FineSim. Those things still live
With a competitor, though.
with a competitor.
So you have your hands everywhere.
A lot of the guys actually in the characterization groups in Cadence are originally from Silicon Metrics, right? So if you look at a lot of the characterization people, they are, because that's where we were hiring specifically, right? So their resume reads characterization. So that's where they ended up in all these big commercial companies.
What did you get right and what did you get wrong as an entrepreneur?
I think you can get too caught up in the outcome, right? And not think enough about, like I said, that process of realizing that you can only control what you can do is a gradual process, right? So we went through lots of angst about thinking about whether we're going to be able to land this customer, whether we're going to be able to make this, get the next VC interested in the next round. You spend so much time worrying and trying to project across all those unknowns that you don't have enough bandwidth to do what you need to do now, right? So I think we got that right later on in the process, but in the beginning we went through a lot of angst on that. So it was a growing process for all of us.
Interesting. And Guru, you exited in 2003.
Mm-hmm.
Did you get rich doing it?
Well, I made money. It was a nice exit. I put, my notion was I would take a third of that money and put it for my next startup, right? So that's what I did. Spent a year and a half on another startup with a friend of mine who actually worked with in AMD, right, on this K5. So Sandeep, he's actually here in the Bay Area. Sandeep and I did, he actually started this company called Synchronous Design, which was around zero skew clock tree synthesis. Again, interesting idea. Somewhere like a bridge between synchronous and asynchronous design, right? So the idea was that you could have staggered logic and clocks so that you can reduce the amount of buffering that you had to do. So we spent a year and a half building that software, and we did that till 2005, until 2007. So we actually exited in I left Magma in 2005 and worked for a year and a half. And that's where a third of my money went. But then 2007 happened. All the money dried up. We weren't able to raise money. And I decided that I had to go work for another company. So I joined Cadence.
Before we talk about your Cadence journey, please tell us a little bit more about your wife.
Nepali is, she's a professor, economics professor. I met her in Syracuse. Um, Pursued her diligently until she said yes. Meeting her was like a door opened in my life, right? Before that, it was very inward looking. It was all about what I saw and what I could do. And when I met her, her level of connection to the world was eye opening. She is very empathetic. So the notion of how what other people feel was much more important for her, right? That idea of selflessness. So that was eye opening for me. Of course, she was way smarter than I am. She was much better read. She had all these experiences. She grew up in a more affluent, under more affluent circumstances. She was exposed to a lot more. So that was eye opening. So yeah.
Guru, you joined Cadence in 2007, right? And you've stayed with them, what, 18 years now?
Yes.
What kind of work did you do in the first few years at Cadence?
I joined what's called the OpenAccess database team. So OpenAccess is there is a vision of there's a guy called Joe Santos who is now retired. But the idea was that you could have a open source EDA database, right? I mean, EDA databases are not like SQL databases, right? The scale of the data that you have to hold in these databases is much larger. It is very designed to doing the kind of things that EDA tools want to do, right? The kind of navigations through the database that you have to do. It is not just joins and sorts. So he started this in 2000. And again, credit to Cadence, right? They pretty much funded the work, right? Cadence was the reference implementer. So OpenAccess is now managed by a coalition called SI2, based in Austin. Cadence was the reference implementer, still is the primary reference implementer, right? So for many years, they had 25 people working on software that didn't make any money, right? It was primarily a lot of startups benefited from having access to an industrial strength database. So I spent 6 years there as an architect. That was actually 4 years before the OpenAccess team got folded into what we call the Virtuoso team. And so I was there for, again, up till then, I was in a development team, at least in my startup, I was the one driving, right? I was basically not telling people what to do, but kind of being the technical lead. Now here I was in a room full of technical leads, right? All of whom were smarter than me, right? And all of whom loved talking about software, right? So we would spend hours talking about modularity, encapsulation, risk management, and OpenAccess had all these unique challenges of compatibility, and you had to worry about what happened to software that was delivered 6 years ago versus what's going to happen 6 years in the future. How are you going to keep, shared object level compatibility and all those kinds of, esoteric things that if there was anyone listening in and listening to us argue, they would say, what the heck are these guys talking about? Why are they wasting their time? But it all made sense to me. So yeah, I spent my first few years was on OpenAccess. I did work for the Virtuoso infrastructure team, primarily on the geometric side. Redid what's called the region search, which is essentially what happens in a lot of these EDA tools, especially the interactive tools, is that you have the database, which is the organization of the data on disk. And then you have the region search structure, which is essentially the organization of the data that is efficient for things like proximity search, right, or neighborhood search, because that's what EDA tools do. Like, for example, a DRC check would basically,
Optimization, right?
or a DRC, right, design rule check, is looking in its proximity, right? It's trying to figure out what is in my proximity. Am I violating any manufacturing rules? All those are dependent on an efficient region search. So, I was telling you earlier about those discontinuities that come up, right? So there was a discontinuity that came up in terms of a design style, and suddenly the region search that was being used in Virtuoso up till then was not able to deal with it, right? So that was a crisis. And so I went in and redid the data structures, the plugin, and worked with a couple of guys, and it's still being used, right? That's the region search structure that is being used.
Guru, that is very interesting. So fundamentally, if you look at the EDA tool, then you do a pass, you find points that are important, and then you store information and then index it to be used later on. And that's, I mean, the EDA database seems to be a very core part of that data organization, right? To be able to then do these kind of searches and then you do a second part and look at constraints. Is that the structure? Like take a pass, store?
If you look at an EDA tool chain, there are more than 100 tools involved, right? So, and then within each, so there are three big pieces. There is synthesis, which is essentially taking some intent that you have, right? So you want to say, I want to design a microprocessor with these functionalities. You're going to express that intent in some language like Verilog, right? That's going to get synthesized. Now there are pieces in there where you're going to have things like analog blocks, right? Transceivers, Bluetooth receivers, right? I mean, these radios that you can't really design with digital software. You have to do that manually. So now you got to take both these pieces and put them together. So there's a synthesis and design piece. Then there is simulation, right? You got to see if it actually works, right? And you got to be doing that by running it. You're not building those yet, but you're doing it against models. So those models are, representations of what is actually happening in the physical world, right, in the foundry. And then finally, there is verification, right? Did what I intend to build actually get built? So there is the layout piece where you are actually, converting that intent into actual wires and traces and placements. And there's simulation, and then there's verification. So data is going through a transformation, right, as it is going along. What starts off as Verilog becomes some kind of compiled netlist, which will become some kind of layout, which will become some kind of manufacturing database that is sent out to the foundry, right? You're basically talking about hundreds of iterations that designers have to do, right, of this data through these tool chains. Data is evolving. Each tool is going to have different ways of accessing the data. Each tool is going to want to put its own decorations on that data. So you need to have some kind of database that supports all these different strategies. And you got to have a database that can be used years from now, because the chips might still be manufactured years from now, that you might still want to do an ECO on years from now. So yeah, you have data is central to that whole tool chain.
And then you were an architect with OpenAccess, and then how long did you do that, Guru?
Well, I didn't really leave, right? I mean, our organization got folded in as part of a larger organization. So basically, we went from a semi-autonomous group within Cadence to becoming just part of a business unit inside Cadence. And I was in Virtuoso till about 2022.
And what kind of work did you do, from about 2015 to 22?
It is, again, a series of projects to address things like, discontinuities, right? there was one on, if you look at multi-patterning. Multi-patterning is the ability for you to have, off DRC traces on the same layer, right? So you can basically have multiple depositions on the same metal, right? So, and they are designed to have very specific constraints. So what we call MPT, right? So this multi-patterning strategy required changes, right? It required us to do, it brought in design much closer, basically made DRC necessary to do as part of design, because it's not possible to get design right and then do DRC. You had to do DRC while doing design, right? Otherwise, you end up doing your design, DRC says no, you make a fix, you go back, it says no, keep staying in that loop. So that is one thing that we had to do. There were other projects related to kind of integrating digital and analog blocks. If you look at digital blocks, they're huge, lots of devices. You look at analog blocks, not as many devices, but much more complex. But if you look at something called DOT, right, digital on top, now you have mixing digital and analog. So how do you put the two of them together? So you have to write some glue software to be able to bring those pieces together. So I did some of that mixed signal kind of work. So it was like a series of projects in Virtuoso.
When did you first see that, that explosion? I mean, it's been happening for a very long time now, but let's talk specifically about AI. The explosion of, AI designs. When did you first see early signs and that having an impact on EDA itself?
So in 2022, I moved over from the IC side into the packaging side, right? So, and my focus was on improving the scalability of our packaging tools. And I was asked to do that, right? Because the tools were not able to keep up with what the AI designers were doing. Especially, and this is coinciding with the entry of traditionally silicon foundries into the packaging business, right? So before there was this very clear separation where the foundries stayed on the IC side, and you used photolithography and all these processes, lithographic processes for silicon on chips. And you had the OSATs, right, who would use laminates for boards or organic materials, different kinds of, not silicon, right, because silicon was too expensive for those kinds of devices. I think, about a decade ago, you have all these foundries now beginning to see the potential for growth outside ICs. So they are now bringing silicon processes into packages, into what used to be the PCB side, right? So that's why you have your iPhone is able to fit more and more electronics inside, because what used to be PCBs are now chips.
Yep.
And the reason you can do that is because what used to be done on a laminate process is now done on silicon. But of course, the number of people who can afford to do that are very few, right? It's only the Apples of the world who can afford to spend millions of dollars on a shuttle run through TSMC and use their advanced processes. Everybody else would still be on, the more commodity side. But if you look at, that's when I really got exposed to, that whole world outside the IC. When I was on the Virtuoso side, I'd begun understanding that because I was doing some of the packaging work inside Virtuoso, and I begun realizing that, the world doesn't end when the IC stops, right? There's a whole world outside which is, much more closely connected to the end user than the world of the IC. And that world is changing fast, right? If you look at the secular growth in packaging, if you look at the secular growth in the world outside ICs, you're talking about 20%, right? Mom and pop shops in Asia are designing packages, right? They're not designing ICs, but they're designing packages. There are just this explosion of users on the packaging and the PCB side. So I think that's when you began realizing that there is no way that the tools that were designed for PCBs, where there were a few thousand surface-mounted devices, would work, right? Because now you're talking about packages where the number of devices is getting up to an IC scale. So you really need IC style design strategies and software to be able to do that. But you're talking about an entire market that is using packaging styles, right? For example, you don't have orthogonal routing, right? On the packages, they're used to doing circular wire, circular arcs. Well, software on the IC side is not designed to do that. You don't do that on silicon, right? You don't do circular arcs on silicon. So you have to rejuvenate the software, right? You have to kind of rebuild, take the existing software and change the, its ability to handle, go from a few thousand devices to tens of millions of devices. So that's when you begin really understanding what this whole revolution is doing, right, to us. We are the ecosystem enabler for all of the AI hardware that's being developed, and that is putting the pressure on us to be able to handle all these huge devices.
When you first said that your number of customers are increasing from 1,000 to, I think you used the number of million or 10 million, I was very surprised. But, that is coming from the diversity on the packaging side.
It's mostly coming from the diversity on the packaging side. On the board side, packaging side, I think you look at China and India, right? If you just combine the two of them, the amount of domestic, the need for domestic electronics is going to be huge, right? I mean, it doesn't have to be a commodity part that sells in the millions, right? Or volume that you build in the millions. It can be targeted endpoint devices, and your ability to actually put that together relatively quickly with not a huge amount of knowledge is there today, right? So you have to, and they buy software from various companies and put together the designs and they manufacture it. That's a new customer, right? And you look at the scale in India and China, we have no idea who is actually using our software, right? There's a lot of piracy that goes on, right? Nobody pays for software in India and China. And so we have no idea. It could well have been that in the last 20 years, at some point that transition happened and we just didn't know, right?
So there is piracy in EDA software like the old days?
Oh yeah, huge problem. Huge problem.
I thought everything should be web-based by now with...
A lot of EDA software, the transition has been happening over the years, but there is still a lot of EDA software that is node locked, that is FlexLM based, that can be, broken.
Floating licenses.
Yeah, there are markets in China where you can buy copies of Cadence or Synopsys software on CDs. They used to be on CDs, but now God knows what they are on, right? You can download them. And people don't have any appreciation, right, for software. It is not something that you can see, right? If someone goes in and steals a chair from your office, that's a physical object that everybody would agree that you're a thief, right? And that you should be punished. Software, everyone does that. Large companies in India used to do that. I think less so in the last few years, right? But people would think you're stupid to be paying for software at one time, right? And my argument was always, where do you think the software comes from? It doesn't come from the ether. It's human effort that goes into that. You can quibble about the cost of software, but you can't quibble about paying for software.
think that mindset change is now happening.
It is.
And companies are getting better at
Tracking it.
At tracking it, and then the value creation around it. And the software, you can't do without software. It's such an essential part, right? And
it's not optional anymore, right?
Yeah.
I mean, it's like a chair or a table. You need it, right? I mean, if you are a design house, or even if you are a logistics company, right? There is no way that you're going to be able to do that with the munshi sitting in the back, right? Keeping ledger notes. You're going to have software, and you're going to have software not just tracking, but also managing, guiding, driving, tracking, doing all that stuff, right? So that kind of ecosystem, people I think understand now should be something that you pay for, especially because you need maintenance, right? Software dies, machines on which the software is run go obsolete. You need constant tending, right? And that is maintenance that you have to pay for. I think people get that now.
Guru, we've talked about a lot of different things. It's been a fascinating conversation. We've talked about how designing AI chips themselves, is changing EDA. But there's this new and interesting world of now using AI to do EDA better. Let's start to delve a little bit deeper into that part, Guru. I'm sure there's a lot of conversation going on at the top EDA companies, including Cadence and the industry in general. Where do you expect the most of impact of AI to be in EDA?
So if you think about the transformation process that happens for a design and the EDA tools involved, right? There is a solution generation part, which is basically saying, given a set of parameters, how do I create something that meets your intent, right? So whether it is a synthesis tool that is trying to say, okay, you gave me some Verilog, I'm going to give you some combination of gates that I'm going to draw from some technology that will actually meet those intent. And then it has to optimize it, right? And the optimization is basically saying, okay, given that you have some timing characteristics, given that you some PPA that you're trying to reach, how do I meet that, right? And it's going to make adjustments to logic. It's going to make adjustments to the routing. The same thing on the layout side, right? So in that EDA pipeline, you have all these little loops that go through, proposing a solution, checking if it fits, changing the parameters, right? That optimization process. The number of variables is huge, right? So the search space is huge. You have no idea how much of the search space you're missing, right? So if even EDA software that is written to kind of navigate the search space and be able to find hills and valleys and be able to make sure that they have covered, do enough sensitivity analysis on individual parameters, use principles like superposition to be able to isolate certain parameters. If you can do all of that, but you still are missing a huge amount of search space, right? At some point, I think there will be much better automation strategies to cover more of the search space. I don't think we are there yet, right? I think this is all active research topics, right? I listened to your conversation with Siddharth, right?
Dr. Nath, yep.
Yeah. And it was fascinating because it is that whole multivariable optimization problem is a really interesting space that anyone can kind of think of, right? You can kind of visualize this n-dimensional space which has all kinds of contours, and you can visualize a pebble kind of traversing through that space and trying to find that sweet spot that meets your, it's like a Dali painting, right? Except that it is in a million dimensions. Uh, how do you, you know, go around that space and make sure that you are hitting the right, uh, hitting the right hills and valleys is something that I think AI is going to eventually get better at. Um, what we do is capture some idea and capture it in software, right? So, for example, Monte Carlo, right? You can do Monte Carlo, which is basically saying, well, I'm going to do some kind of statistical sampling, right? And I'm going to hope that I covered enough of the search space. And when the time runs out, that's it, I'm done. Which is not driven by whether you've covered the search space, but by how much time you have, whether to complete the design, a reasonable amount of time to run the tool, amount of computational resources you have, right? It is driven by that, not necessarily by the contours of the problem. I think that at some point, the kind of multivariable sensitivity analysis and search is going to get better and because of the things that AI brings in, right? So that's one area. I think another area is if you think about a typical EDA interaction that the user has, right? An EDA tool interaction. You do something, the tool gives you a report, and then you look at it, right? Based on that report, you decide what to do next. You make some changes, and then the tool does it again. Imagine that there is some kind of interaction between two agents where, when I'm doing that analysis of a timing report, for example, right? I'm looking for, say, total negative slack. I'm looking for certain things. There's a structured set of things I'm doing, right? I'm not necessarily being very creative, right? There is a mechanical aspect to what I'm doing. At some point, I'm going to be creative in terms of coming up with some nonlinear deviation from what I was doing before. But most of the time, the designer is making those kinds of mechanical adjustments based on the feedback they're getting back from the tool, from the static timing analysis tool or from the simulator. They might be looking at eye diagrams, making some adjustments to get the right eye diagram, the constellation diagrams, whatever, right? All that is going to get automated away, right? You can imagine two agents interacting with each other that are fine-tuning their way out of all these little problems. Now, they're going to get to some point and they're going to say, we've done as much as we can. We give up, right? And that's when the human being comes in and kind of changes some big knob and goes off again. That's a very different interaction model. It's a very different architecture that is required of the EDA tools, right? Because now the tools have to kind of split into this, proposal and verify components, right? Where the verify component is carefully examined to make sure that you get it right. But the proposal component is a bit like Gen AI, right? It's easy to come up with ideas. You don't have to be right. So that proposal piece can really come up with all kinds of outlandish proposals, but the verification piece has to be pretty solid. Otherwise, you're going to end up with garbage at the end, right? The verification piece is the one that is saying, stop. No, it's not going to work. This is the real world. I'm the real world. You are in Dali land, right? So I think that it's a very different architecture. That's exciting, right? I mean, I think we are going to get that kind of model for every one of the pieces in the toolchain. The toolchain is not going to go away because there is a concrete need for every piece in that toolchain. There's a lot of glue logic. All that stuff is going to go away. Writing scripts to manage flows, all that stuff that EDA teams used to do, that's mechanical stuff. It's going to go away. But the exciting part about the architecture is, if you look at LLMs, for example, right? LLMs are, in my mind at least, it is a statistical supercharged information retrieval system, right? It is able to approximately, get close to where you are and be able to generate things in that space, whether it is text, videos, or designs, right? At the end of the day, these are details that have to be worked out, but it could do that. So I think that is exciting because that can keep expanding its capability by throwing more data at it, right? You throw more context, eventually that will be able to propose more and more things. But at the end of the day, you got to have a rock solid verifier because your business depends on it, right? You can't say, I'm going to push a button and the machine is going to generate a design for me, and then, my career depends on that, right? No designer is going to do that. As a software engineer, I can't take the code that Claude gave me and say, put it in the code base, right? I'll be stupid because at the end of the day, I'm responsible for the code.
Yeah.
So I have to understand that code and I have to be able to make sure that it does what I asked it to do. Same thing with the designer.
Interesting, Guru. Guru, in the current state of how the ADA industry is using AI, how are they using it for, say, something like design space exploration? Is there a traction of using AI there?
Yeah, I think there are. Again, design space exploration can happen in multiple contexts, right? And there are many contexts where it's a little easier to do, right? What I would call the fringes, right? If you are closer to the text side on the intent, you can explore more. If you are closer to the manufacturing side in terms of actual traces, you can do more, right? Because on one side it's images, on the other side it's text, and that kind of fits in more naturally into the commercially available models. But once you start getting into the middle, you're talking about this weird mix of logic and where just having a graph is not enough because that graph is not a canonical representation of a design. I can have 10 different graphs or 100 different graphs and they all could mean the same thing, right? Now you're talking about a much harder exploration problem because it is not just points in space but regions in space that are familiar, that are similar, and the regions might not be in that metric space close, right? It's not clear to me that we understand that enough. That's why I was so fascinated with your discussion with Siddharth, right? When he was talking about how you can navigate that space. Hard problem.
Yeah, he's since gone on to join Google DeepMind, working on trying to solve that problem. What about the complexity problem, Guru? Do you think AI could help with gaining a better understanding of what's going on in itself, the analysis part?
Yeah, I think one of the things that was impressive to me when I started using, software like Claude or ChatGPT is its ability to just give you a narrative, right? Convert code into a narrative. So I could throw a complex file at it and it would come back with a description of what that file does, right? Not just basically gleaning it from the comments, but actually understanding what the code is trying to do. At the end of the day, it is easier to read a narrative of or hear a narrative, right? Imagine that you're hearing this narrative. It is easier to do that than to look at code, right? Code, you have to keep a lot of context in mind. You have to have, relatively specialized knowledge. Plus, you have to have the legacy understanding of what is there behind it. There's a lot of things that go on into internalizing what a page of code is trying to do. Of course, there are, as you get do more and more of it, you get better. But a narrative is a little better tool to be able to get that understanding. especially if you are looking at new software or software that you haven't seen before. So I think that process of converting uh, existing code into a narrative and being able to then manipulate the narrative and then use that as a spec to make changes. I think that's a very attractive, uh, you know, future. I think there are a lot of trust barriers that you have to get past, right? A, did you understand the code right? Or are you hallucinating, right? You looked at a map, associative array, and gave me some BS about what that map is being used for. Did you cross check, right? Because if I'm going to make decisions based on what you tell me, I better trust you. I don't think we've crossed that trust barrier yet.
And you don't even have the data for the run, right?
Yeah.
You're just looking at from code, and
Yeah.
Some things can, unless you have the data in a real run, you can't even know, right? So are you accounting for that, right?
Yeah. So I think eventually it'll get better, right? It'll cross the trust barrier. And then that narrative is something that you can use to drive change. And that change is something you can trust. So, I mean, that's my kind of dream of the future, right? That you have the ability to, and it's, in my mind, it's an evolution of something that has happened. Like, if you think about, abstraction, object orientation is an abstraction, right? The ability to go from writing procedural code in C or Pascal into C++, where you're thinking about, objects as opposed to the actions, is a big change. It's a huge change because there are a lot more actions that people can do than there are people, right? Than there are objects. So it allows you to model the world better. This is one level further. Right? This is now basically saying, okay, you're talking about, just your intent in terms of the groups of people and the actions, and you're expressing that intent in a natural language, and you are finding ways to convert that automatically into something actionable. And that's very attractive.
Guru, thank you for sharing that perspective. It's very powerful. Guru, let's talk about your vision for the future. Where do you see EDA evolving, and how do you see EDA evolving in the next 10 years or so?
I think it's going to get much more, the architectures are going to change. So I'm much more interested in the architecture, much more interested in, how the tools are evolving as opposed to necessarily what the tools can do, right? What the designers can do with the tools. That's my natural interest. I think the architectures inside the tools are going to become much more distributed, much more cooperative. That model that I was talking about, that back and forth model, that opens up more opportunities, that allows you to explore more of the search space, that allows you to give more of a guarantee that you're generating things that are, bound to work, right? I think that it's exciting that you can now go through the EDA toolchain and get designs that will work, not just when they come back from the manufacturer, but in the real world, right? That continue working over extended periods of time under completely different environmental conditions. That's exciting. I think EDA is going to be able to give a much more of a guarantee that what is actually coming out will continue working in the real world for longer.
So you expect yields to increase?
I would think so, because again, I would assume foundries will also be using similar strategies, right? Everybody is going to be, getting more out of what they have because they were not able to use all the data that they've been collecting up till now. And again, as they are able to, as their models are able to mimic the physics and the chemistry of whatever they're doing better, and who knows biology, right? It could be biological computational units coming too, right? As those models are more accurately representing all that hidden stuff that we couldn't represent today, the yield should improve, right? Especially what's also going to happen at the same time is more money is going to go in, right? It's more investment. There is, more automation, less room for human error, right? So there is all these factors that says yields are going to go up, number of design starts are going to go up, amount of the volume of electronics or semiconductors that are coming out is going to go up, and the quality of the semiconductors that are coming out is going to be better, right? I think that's all natural evolution of things.
Well, these are exciting times, Guru. In the 1900s, it used to be the railroad companies were the largest companies in the world, and then the financial companies, and then the oil companies. For the first time ever, it's a hardware company that's the most valuable company in the world, right?
It is. It's amazing. My favorite book was this book called The Soul of the New Machine. Have you heard of that?
No, tell us more.
So it's a book by this guy called Tracy Kidder, and it's about this a company called Data General, which was competing with Digital Equipment Corporation, neither of which exist today. So this was in the 80s, right? And so the Data General, I think it was the MV8000, so they were getting competition from DEC, right, Digital Equipment Corporation. And so they started off this whole different unit in North Carolina to build a new microprocessor. And they were going to build this whole new machine, not just a microprocessor, right? It's a whole system. And so they were, all the brains were in North Carolina. All that were left in, I think it was Boston, were a few senior engineers. They decided to do a skunkworks project called Eagle. And this book is about the evolution of that whole design and how they, and then the subsequent generations of Data General machines were all based on that design. It's the first time when I read that book that you could actually see drama in design. You could see the people being highlighted, right? The emotions in raw display. You could talk about how, you could hear these people arguing about whether a bit should be high or low, whether a transistor should be placed here or there, whether functional partitioning should be done at this level or that level. Like these were life and death discussions. It was a movie. So I remember reading that book and going, wow, first time I'm actually seeing engineering as actors in a dramatic movie. I think that's what the kind of experience that we're having at a large scale with NVIDIA being so prominent is engineering is king, right?
Babies are going to grow up using GPU terminals as memories of their childhood. Oh, those were the times they used to do this stuff through, on-chip SRAM. Who knows what? Exciting times, group. What would it take for a young engineer who's just entering today to be successful, Guru? You've seen the whole journey. What does it take to be successful in EDA today?
Engineering is really interesting, right? Because it's such a long path. To get a job in a company like Cadence or an EDA company or a scientific company, you got to have masters. So you spent 5 years, 4 years in bachelor's, 2 years of your master's, sometimes another 3 or 4 years doing a PhD. That's a long ramp. So by the time they are in a company like Cadence, they have already ticked off all the boxes. A, you're curious. B, you pay attention to detail. C, you're always prepared for failure. For me, the young engineer who's coming in has to be curious and motivated and not afraid to ask questions. Right? There are three primary characteristics. Uh, don't be afraid to look stupid. Don't be afraid to fail. Because your objective is to learn, right? And everything else is secondary.
Well, we've talked about so many interesting things. Is there anything else that you would like to share with our audience?
You know, we've known each other for a while now, and for me, this is the closest I've had to a group of friends. We are a group of friends that have been meeting together now for 15 years. This is the closest set of friends I've had, right? So we share everything. For us, coming out every weekend playing tennis is a release of a kind. It is something we look forward to. You can feel it when you don't come for a week, right? You feel like you are missing something. Even when we are not here, when each of us could be in different geographies, we are still texting back, right? It's like family, right? So I think that's what really kept me going for many years. I'm appreciative of that. And so you guys are my extended family. Do you recommend others to develop such a circle that goes beyond work and personal life to have an outlet? I think it is critical, right? You look at the amount of depression in society today, it is all because of loneliness, right? And loneliness happens because you did not invest in creating the community that you want. Your community can be of different kinds, but if you have that community, it can completely transform how you look at life. You can have the most difficult of circumstances and feel lucky. That's what community does to you. Guru, thank you so much. I've enjoyed my conversation with you. Today, we were joined by Guruprasad Rao. Guru is a distinguished engineer at Cadence and a leader in the EDA, electronic design automation space. Guru, thank you so much. You're welcome.